Hello, stat students, and welcome to day 3 of section 9.3. We'll be continuing to talk about tests about a population mean. And we left off yesterday talking about significance tests for paired data. We were looking at this example right here where we're looking at the mean difference in depression scores for 11 subjects after being deprived caffeine. We got through talking about the conditions for this test, but we did not look at the final results of the test, so let's take a look at how this works. Basically, if you'll remember what I said is, for paired data, the mechanics for the test will end up being exactly the same as you do for just regular one-sample data. So basically, you'll still use the same command on your calculator for a t-test, even though it's called a paired t-test instead of a one-sample t-test. But basically, you can use technology to get the test statistic, and you can find that the area to the right on a t-distribution with degrees of freedom 10 is 0.0027. And these three things I have highlighted here are basically the three things you need to make sure you have written down when you use your calculator. You need the test statistic, you need to write down the degrees of freedom, and you need to write down the p-value. You'll notice that it's an extremely low p-value. That will lead us to our conclusion that our p-value is less than alpha. We do have convincing evidence to reject the null hypothesis that the mean difference is 0. We can therefore conclude that depriving these caffeine-dependent subjects of caffeine caused an average increase in depression scores. Notice what I've got highlighted here. The wording of this conclusion is the conclusion can just be made for these caffeine-dependent subjects. And that's because of how we created our data. If you go back here, you'll notice these were volunteers. So these people were not randomly selected, which means my conclusion cannot be made about a general larger population. It can only be made about these people. So does that mean I should have said we don't meet the random condition? Well, no, there was something that was random, and that was the order of the treatments. So it was a randomized experiment, it's just that these subjects were not obtained through randomization. So I'm still fine running the test, but in the end, my conclusion can only be made about these people. Few follow-up comments about this example. Although the differences in the depression scores for these subjects are independent, the two depression scores for each subject are not independent. And when you're working with paired data, the independent condition only refers to the differences. So it's just that these scores are independent of each other. These are not going to be independent of each other because they are depression scores for the same person. So if one of these is higher, we would maybe expect the other one to be. But when working with paired data, it's just the differences that need to be independent. We could have calculated the test statistic in the example using the following formula and obtained the p-value using table B or our calculator's tcdf command. The calculator-only method is acceptable. Be sure to report your degrees of freedom with any t procedure, even if the technology doesn't have that on the screen. Make sure you write it down. These subjects in this experiment were not chosen at random. I mentioned that already. We cannot generalize our findings about all caffeine-dependent people, just the people in this study. However, because it was a randomized experiment, we can make a cause and effect conclusion. So we can say that for these people, it was the caffeine pill or placebo that did make the difference. Remember, a confidence interval gives more information than a significance test. A 90% confidence interval for the difference in depression scores would be as follows. So we are 90% confident that this interval captures the true mean difference in depression score. That is, the data give convincing evidence that depriving individuals like these caffeine do result in an average increase somewhere from 3.5 to 11 points on the depression test score. So you can see that since 0 is not in this interval, that's, we can rule it out, and this gives us a plausible range of values for the amount of increase we would expect to see in depression scores. All right, moving on. Let's talk about using t-tests wisely now. Significance tests are used kind of all over the place in research in many fields. New drugs require significant evidence of effectiveness. Courts ask about statistical significance in discrimination cases. Marketers want to know whether a new ad campaign significantly outperforms the old one. Medical researchers want to know if a new therapy performs better. Now, in all these cases, statistical significance is valued because it points to an effect that is unlikely to occur simply by chance. However, carrying out the significance test is really quite easy. You just use your calculator. However, using them or knowing how to use them is not so simple. So some things to keep in mind when interpreting significance tests. We'll talk about 4 things here. First one, statistical significance and practical importance. When the null hypothesis can be rejected at the typical levels, there's good evidence of a difference, but that difference may be very small. If you have a very large sample available, you can detect very tiny deviations. For example, let's say we're testing a new antibacterial cream on a small cut made on the inner forearm. We know from previous research that with no medication, the mean healing time, and that's defined as the time it takes for a scab to fall off, is 7.6 days with a standard deviation of 1.4 days. So we're trying to test whether this formulation speeds up that healing time. So we cut a random sample of 25 college students, we apply the formulation, the mean healing time of these subjects is 7.1 days, standard deviation is 1.4. And then we want to, test a claim about the mean healing time in the population compared to our null hypothesis of 7.6. We want to see if the sample provides convincing evidence that the healing time is less than 7.6 days. So an examination of the data reveals no outliers or strong skewness. The conditions are met. We carry out, here's the test, here's the test statistic. The p-value is 0.04. That p-value is less than alpha, so we reject the null hypothesis, and we conclude that the healing effect is statistically significant. However, this result isn't really practically important. You'll notice in the sample, the mean healing time was 7.1 days, compared to the population that we're already familiar with as 7.6 days. That means the scab will fall off half a day sooner, and that practically isn't really that much of an increase in healing time. So that's the first thing we have to be careful of is, sometimes if we're detecting a very small difference, not really important, and they probably won't put this healing cream on the shelves. Next, don't ignore lack of significance. So there's a tendency to infer that there's no difference whenever p-value fails to attain the usual 5% significance level. Now, in some areas of research, small differences that are detectable only with large sample size can be of great practical significance. When planning a study, verify that the test you plan to use has a high probability or power of detecting a difference of the size that you hope to find. For example, in an experiment to compare methods of reducing transmission of HIV, subjects were randomly assigned to a treatment group and a control group. The result, the treatment group and the control group had the same rate of HIV infection. Researchers describe this as an incident rate ratio of 1.0. The ratio above 1 would mean that there was a greater rate of HIV infection in the treatment group, while the ratio below 1 would indicate a greater rate of HIV infection in the control group. The 95% confidence interval for the incident rate is 0.63 to 1.58. Saying that the treatment has no effect on HIV infection is misleading. The confidence interval for the incident rate indicates that the treatment may be able to achieve a 37% decrease in infection, because this is 37% below 1. It might also produce a 58% increase in infection. Clearly, more data are needed to distinguish between these possibilities. So just because they observed no difference does not mean that the study was useless. Statistical inference is not valid for all sets of data. Badly designed surveys or experiments often produce invalid results. Formal statistical inference cannot correct for flaws in the design. Each test is valid only in certain circumstances, with properly produced data being particularly important. Does music increase worker productivity? You wonder whether background music would improve the productivity of staff who process mail orders in your business. After discussing the idea with the workers, you add music and find a significant increase. You should not be impressed. In fact, almost any change in the work environment, together with the knowledge that a study is underway, will produce a short-term productivity increase. This is called the Hawthorne effect, named after the Western Electric manufacturing plant where it was first noted. So the significance test correctly informs you that an increase has occurred that is larger than would arise by chance alone. It does not tell you what other than chance caused the increase. The most plausible explanation is the workers change their behavior when they know they are being studied. Your experiment was uncontrolled, so the significant result cannot be interpreted. A randomized comparative experiment would isolate the actual effect of the background music and so make significance meaningful. And finally here, beware of multiple analyses. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study for search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. Don't search for significance, and here's what that means. Might the radiation from cell phones be harmful to users? Many studies have found little or no connection between using cell phones and various illnesses. Here's part of a news account of one study. A hospital that compared brain cancer patients in a similar group without brain cancer found no statistical significance association between cell phone use and a group of brain cancers known as gliomas. But when 20 types of glioma were considered separately, an association was found between phone use and one of these rare forms. Puzzlingly, however, the risk appears to decrease rather than increase with greater mobile phone use. So let's think about that for a moment. Suppose that the 20 null hypotheses for these 20 significance tests are all true. So basically there are 20 different types of glioma and we run a separate significance test for each of them. And let's say the null hypotheses for all of them are true. That means that there is no significant difference. Each test, though, has a 5% chance of finding significance at the 5% level. That's what alpha equals 0.05 means. That would be a type 1 error. There's a 5% chance of making a type 1 error. So that would mean we're going to wrongly think that we have significant results even when the null hypothesis is true. So we would expect about 1 in 20 tests to give significant results just by chance, and therefore making a type 1 error. Running one test and reaching that 0.05 level is reasonably good evidence that you have found something. Running 20 tests and then reaching that level once is not significant evidence. We would expect to make 1 error out of 20 because that's 5%, and that's 5% of the time. So we should not be surprised that 1 of the 20 was found to be significant. So that's it for our using test wisely, and that's it for section 9.3. So make sure you've got the 9.3 homework done. Here are all the topics we covered in 9.3. Be ready for that tomorrow.